Okay, so today I would like to spend maybe the first 20 minutes or shorter just to finish the topics about subcontracting, about inheritance and contracts. And then I'm going to move to a new design pattern which might interest you quite a lot. I don't think you have learned state pattern before in your 2030. So it's going to be something completely new. So you're going to find it interesting, hopefully. Okay, let me just go back to what we left off from last time about inheritance. When we talk about inheritance, we really talk about code accumulation and substitutability. So in general, when you're expecting some objects of a certain type, you can always substitute it by any descendant objects. That's what we have learned so far. And we just want to talk about how you can, when you are designing your contracts, especially precondition and postcondition, how can you judge if certain contracts are really appropriate or not? So I'm going to talk about two mechanisms you can judge. One is when you're designing your contracts, you have to do some logical proof, like what you did in 1019, which I'll show you some example. The proof that you will be required to do in this course will not be as difficult as what you did in 1090, I promise. But you have to do some basic, which I will show you. And then we also want to see that when you have contracts in both the superclass and subclass, how are they checked together at the runtime? So these are the two topics I would like to go through before I move on to design pattern. Okay, let's again look at the example I had over there. Let's just see this. This is the principle. The principle is simply here. You want to make sure that every time in the subclass, you do not require more than what the superclass will require in terms of the precondition. And also, you do not insure less than what can be insured from the superclass. So these are the two principles. Let's see one more. Let's see the example that we started last time. Okay. Let's have a look at this first version over here. Okay. Let me draw your attention to precondition first. Precondition. So this one, alpha over here, is the precondition at the superclass, and this alpha and gamma. So this is at the subclass level, okay? Intuitively think of this. So that's why it is so important to realize this diagram over here, okay? Let me just show you again the architectural diagram. Okay, this diagram here, you can see any phone user, when they first declare their variable over here, it's of static type smartphone, which means all their expectation comes from the contracts of smartphone, which is a superclass. And then under the hood, you may substitute the smartphone by any of the descendant classes. But why would this such substitution work? It depends on how you design your precondition and postcondition in the subclass. Okay? So now let's see one case where the pre and postcondition are appropriate, and another case where it would not be appropriate, just to give you some feeling. But there will be a certain logical rule you have to follow. Let's see over here. Let's say over here. Let me again remind you about the diagram over here. Let's say you have some user over here and they are trying to use some smartphone. Okay. However, under the hood, let's say the smartphone, let's say it always say, if you want to use the get reminders feature, you want to make sure the battery level is always larger than or equal to 10% at least. That's a precondition. Okay? So now, since we say before when we talk about polymorphism, you can safely just substitute the smartphone by another instance of any of its descendant classes. In this case, let's say it's iPhone 6s Plus. Now, in this case, we have the same feature, get reminders. You can see that over here. The same feature. Is the precondition over here appropriate or not? How do we judge? Okay, over here you can see require, over here, the battery level has been redeclared to say it's larger than or equal to 5%. Okay? Now, intuitively, let's think about it, and then I'll show you the logical rule, how you should prove it. Intuitively, if I used to be a smartphone user, I always expect that the battery level to be larger than 10%. If somehow I change my phone from smartphone into iPhone 6s Plus, is it going to give me a shock? No, right? Because now you can see the battery level is even more tolerant. So what I expect before, my battery level should be 10%, 11, 12, 13, 14, and etc. Would these inputs still work for the new precondition? They would, right? Because 10 is larger than or equal to 5, and 11 is also larger than or equal to 5. Let's think about this logically. What does that mean? That means when we have battery level larger than or equal to 10%, that logically implies the battery level is larger than or equal to 5%, right? Logically speaking, right? So this is the require from smartphone, and this is the require from iPhone 6s Plus. Okay, so for precondition, you want to make sure this is how you read it. This is how you interpret that. If the client is able to satisfy the precondition in the superclass, that implies they should also be able to satisfy the precondition for the subclass. Okay, so that's why you will see that over there in the slides. I show it to you. There's something you should prove that alpha is over here. The require in the superclass should logically imply gamma over here. Let's see something that's not appropriate just for contrast. Okay, let me just go there, over here. Now, let's consider a different case. Let's say over here the require is the battery level is larger than or equal to 10%. And at the subclass level, it's now not really not more tolerant, but it's more restrictive. So now we ask ourselves the following question. Is the precondition of iPhone 6s Plus okay or not? We try to see if the following implication will hold or not. We try to say if the battery level is larger than or equal to 10%. So that's from the parent class. Does that imply the battery level is larger than or equal to 15%? It doesn't. There will be certain counterexample you can find. For example, let's say if you have, let's say 11%. 11% is going to satisfy the precondition for the smartphone. However, if you change your phone from smartphone to iPhone 6s Plus, you will get shocked because 11% is not going to satisfy this. No. So that's not appropriate. Okay? That's how you interpret the precondition. So every time if I want you to judge if the precondition you have in the descending class is appropriate or not, you want to somehow show this logical implication. As I said, for this course, I think you only have to deal with things like this just for getting some intuition, getting some idea. But of course, in general, the Boolean expression you have can be very complicated, right? But that's just an example to show you. Questions about precondition? Yes?
So you don't have really precondition for the redefined method since it's relying on the stronger precondition over there.
Aha, yes. But there might be some cases. It's a very good question. The question was, if we know that, logically speaking, the precondition in the parent class should be stronger, more restrictive. In that case, why do we bother to have the precondition in the subclass? The reason is there might be some cases where we want to relax the precondition. We want to make sure to say that now, when I'm using this particular sub-instance, because we want to relax, we want to get a little bit more less restrictive. You will see example like that. Yeah. But there will be cases you need that. There will be. Mm-hmm. But the bottom line is you cannot strengthen the precondition. You cannot make it more restrictive. Okay. And now what about postcondition? Let's look at the postcondition. Postcondition a little bit the opposite, right? Let's try to read this. Let's see the OK version. Let's say in this OK version over here, for the smartphone, we say that for the get reminders feature over here, every event in the result you return, they must happen today. Every one of them. Okay? And then you want to make sure if I'm used to this particular feature for a smartphone, if I change to a iPhone 6s Plus, I want to make sure this feature can provide to me as at least this surface as before, and no less. Okay? So the logical implication is going to be a little bit the opposite. You're going to turn it around. Okay? So now let's see over here. This is what we have in the subclass. So now we're trying to say everything you have in the result, in the subclass that's returned, it should be today. Not only that it's today, but also it should be between 9 and 5 p.m. This is what it has. Okay? Now, how do we judge if this is logically sensible? Okay? How do we judge that? Let me show you the formula first. So the formula, if you see the next slide, is going to be, we want to make sure if you satisfy the post-condition for the subclass, that implies you also guarantee you satisfy the post-condition in this superclass. So you can see the opposite. You want to make sure we provide just as much as surface as before. We don't provide anything less. Okay? Let's see, in this case over here, how would you judge, right? So now, in this case, let me just write it on the top. Over here, you can see this is one formula over here. It's for all quantification. And how would you do that in iPhone? You can use across all, okay? Let's see, let's only focus on this particular body over here. So that means E happens today, and E happens between 9 and 5. Does that imply this post-condition over here? It is E happens today. Do you see this is actually holding this implication here? It is not? Really? Okay, what about we review some logical law? There will be some laws you need. Why don't I just have a blank page so I can collect all the formulas for you that we're going to need. Okay, some logical law you might need. If I have P and Q, that implies P. And also P and Q also implies Q. Okay, that's what you have from before. I wouldn't go, you can easily prove it by using a truth table, but let's not go there. Okay? Okay, so now you can see that this part over here is really the same. And then you're just having more. So not only that you will make sure it's today, but also you make sure it's between 9 and 5. So you're ensuring more. So now in the iPhone 6s Plus, what we can do is we will not give any shock to the existing user for the smartphone, because we'll always give them only the events today. Okay? Any question about proving this? Any? No? Let's see one example where it is not appropriate. Okay? For this one over here, you have this one over here and this one over here. I can give you a little bit hints. The tricky bit is now we say or. So now the question is, let's try again. Again, logically speaking, we want to make sure whatever you have in the subclass, if you can guarantee that, that should logically imply you actually also guarantee what's really promised in the superclass. Okay, let me write it out. So that means this one first. E happens today, or E happens tomorrow. Does that imply E happens today? Is that the case? That's how you judge, of course. If you don't think that's the case, why not? You gotta give me some counter example. Yes?
We have an or statement. If it happens tomorrow, then it wouldn't it happen today.
Exactly. That's exactly correct. So let's now, okay, that's exactly correct. The reason is, so now this one, no, it does not hold in general. Because if E happens happens tomorrow, If E happens tomorrow, that would be the counter example. In which case, the antecedent will be true, and the consequence will be false. So true implies false, you'll be false. Okay? That's one example for you to judge. Okay. Any question about this? So this is just one example to show you, if I give you anything arbitrary, all you got to do is try to identify what's in the superclass, what's in the subclass, and try to see how you can state the implication there and see how, if you can prove it. The ones I'm going to give to you, either in the test or in the exam, will be somehow straightforward. I just want to make sure you know what the laws are. Okay. Guys, any questions about this? Yeah. Okay. Since it's a little bit dry, so I do expect that you can approach me later if you do have trouble figuring out. Okay. So I'm going to go a little bit fast. Okay. So that's about how you judge. You can also read through the slides. Now, I just want to talk a little bit more about how you can do this programmatically, okay? So what we just talked about was, if I give you something on the paper, or you're doing the design by yourself for your project or for your lab, how can you judge if the precondition or postcondition in the subclass is correct or not? That's how you do the proof in the implication. What does IFO do for you at the runtime? Okay? First of all, syntax-wise, if you're trying to redeclare or try to somehow to add more precondition in the subclass, you have to say not just require, you gotta say require else. You will see why they chose else in just a moment. And also, for the postcondition, you gotta say ensure then, rather than just ensure. You may run into a syntax error when you only put require or ensure in the subclass, maybe, okay? But that's how you fix it. You gotta say require else or ensure then. Let's see why it is the case. And there's some rationale behind. I'll try to explain to you. Okay. So now, IFO at the runtime is going to do the following checks. Let's say you declare some new precondition or new postcondition. Okay. Let me just use a diagram to show you. Okay, I'll go there. Let me just go to this last slide directly. Okay, let's say in this case, let's just talk about the rule first. Let's say we have two classes over here. We got foo and we got bar. Foo is a superclass where we got original precondition, original postcondition. And we also got bar over there. Bar inherits foo and redefine the feature called F. So now we have F actually got contracts in both the superclass and subclass. For F over there, we say require else some new precondition. And then for postcondition, we say ensure then, some new postcondition. Okay? So now you can see we got two preconditions there, and also we got two postconditions there. But how do we check them at the runtime? Okay? Let's see how we can do that. Basically, what IFO does at the runtime is to make sure if somehow you make some design mistake, you want to make sure it doesn't create too much disaster. Okay? For example, let's say what we said before was, if the new precondition there, the red one, is too restrictive, in that case, your client will get some shock, right? Similarly, if your new postcondition there does not guarantee as much, also your client will get some shock. So now that's why what the IFO runtime will do is that they will combine the green and the red together in a way, using some logical operation. And I'm going to show you that, okay? Now, first of all, let's understand the context here. We got original precondition and new precondition for the require, and we got original postcondition and new postcondition for the ensure. Okay, let's see how we can do the check at the runtime. Okay, let me just go back there and then show you. First of all, for the precondition, they are going to use the or else operator. Remember what we said before, or else basically is like the logical disjunction. And since we are using or else, that's why you see require else. That's how they chose the keyword, okay, first of all. But why are we doing disjunction? Why are we doing this? Okay, let's think about this. Let's say this. Let's think about how we said before, what should be the appropriate design. For me as a client, if I'm able to satisfy the original precondition for the smartphone, I should be guaranteed to use the same service no matter what, right? Doesn't matter how strong or how weak the new precondition is. In this case, this is how you think of it. Okay? If I'm able to actually satisfy this particular precondition in the superclass, I should be guaranteed I should not cause any precondition violation when I'm using the descendant instance. In that case, if I use the or over here, you can see true, which means the original precondition is true. As you learned before, when you say true or something, it doesn't matter what something else is, it will always be true, right? That's why they actually do the disjunction over here. So this is to prevent, to say, if somehow, let's say in the worst case, what can be the worst precondition you can write as a descendant clause? False. Good, very good. Yeah, I should have waited for you to say that. Yes, exactly, false. If you simply put false, that means you want to prevent any client to use the service in the descendant clause. That's very bad. But the IFO runtime can prevent this by simply saying, well, doesn't matter if this is false, because as long as you satisfy the original precondition, the overall result will still be true. So the client can still use the service. That's like a precautionary action. Okay? Similarly, how do you think we check the postcondition? The postcondition has this following intuition. We want to make sure if you actually fail the original postcondition, it doesn't matter what your new postcondition is, it should just fail. So it's kind of symmetric, right? So now it turns out this is how they check it. They will simply use and then. Again, that's why you have ensure then, because we use and then to check them at the runtime. Okay? Now let's think about this. If somehow the new postcondition over there is actually very, very relaxing, very, very useless. What's the most useless postcondition you can write? True. Why true? That means any true evaluates is true all the time. That means whatever you do in the precondition, whatever you do in the implementation there is always going to pass your postcondition. So true is the most useless postcondition. Let's say the descendant clause is very evil. They simply put true over here, but we want to make sure the new descendant clause will still guarantee as much as before. So now, if you have true over here, and then if you actually fail the original post, what's going to happen? You're going to have false, and anything will still be false, which means if you cannot satisfy the original postcondition, there's going to be some postcondition violation as expected. Just to tell you there's something wrong, because the original postcondition is not satisfied by the new descending instances. Okay? Okay, that's kind of the rationale behind the two checking mechanism, right? But any questions? I'm going a little bit fast, but if you got any question, ask me now. Okay, good. Okay, a few more points, and then we could go to the design pattern. But I think this part is also very important. It's not really covering lab test 2, might be in the lab test 3. Okay, so you have enough time to think about it. Okay, so now, I want to say one more thing. You might be saying, wow, it seems so complicated. So what if I simply don't bother to redefine any contracts in my subclass? Well, I would say it might be okay, but you gotta be careful with what you're doing here, okay? Let's say again, over here, we got foo and bar. Let's say for the foo over here, require original precondition. Let's say over here, we simply don't declare any require else, simply nothing here, okay? You want to know what this really means if you did not declare anything. Can you take a guess? If I didn't declare anything under require else in the bar, what does that really mean? What would be the equivalent? Somehow the logical equivalent should be equal to the original precondition, which means even though you as a descendant clause, you don't declare any new precondition, but overall, it should still be equivalent to the original one. But how does this work logically? Okay, let's try to see this. So now if you don't do that, it's as if you declare require else false. Can you see why? Logically speaking, how do we check the both preconditions together at runtime?
This is a disjunction of something, other condition or false. And if the condition isn't satisfied, then we just false to false.
Really? Okay. How about I ask you this way, a little bit logically. Let me come back here. If I have false, okay, let me just use any p or false. What is that? P or false? P? P, right? Which means if the precondition in the subclass is missing, it's as if we declare false over here. That means we still have no idea what the logical disjunction should be at the runtime. So we still have to rely on the truthfulness of the precondition from the superclass. Okay, makes sense. Okay. Similarly, now let's try to see the following. Second case, let's say we did not redeclare the postcondition over there. What would that be equivalent to then? Would that be equivalent to ensure then false or ensure then something else? Why? First of all, why would ensure then false not appropriate? It's and, right? False and anything would just be false, right? So now, I'll just write it down in just a moment. So this will be equivalent to just ensure then true. Because if you try this over here, let's say this is the postcondition in the superclass, and if you simply say true over here, it is still equivalent to P. Okay, that's simply just a simple application of the rule from before. Okay, so it's definitely okay if you just don't want to redeclare any pre or post condition in the subclasses, but be careful what you're doing. Okay. Okay, now one more topic about class invariance. Remember what we said before. Class invariant is pretty much like the post condition for every query or command. That's what we said in the very beginning of the semester. Now let's see how the invariance can be accumulated. Because we say that the post condition is somehow conjoined together, right? From the superclass and the subclass together. Similarly for invariance. Let me give you one example. Okay, so every class inherits the invariant from all the ancestor classes, and then the way we check them is by putting conjunction of them together. Okay, let's see one example, very easy. Let's say we have a class called polygon. And the polygon, the vertices is simply an array of points. Let's say we declare points somewhere. And invariant is simply saying polygon should be vertices that count larger than or equal to 3, right? Should be at least 3 sides. Now, let's say we have a class over here, rectangle. Rectangle, in this case, inherits polygon means it is a particular kind of polygon, right? But now we are trying to strengthen, we are trying to make it more specific. The invariant should be, now we have 4 sides rather than larger than or equal to 3. Now, since the invariants will be conjoined together using logical conjunction, what do you think the invariant would be? That's to be checked at the runtime. Well, if you try to conjoin everything together, what would you get? You have this is from the superclass, larger than or equal to 3. This is from the rectangle class. And what you end up checking was just, you got exactly 4 sides, right? Now, this one's easy. Now, I got one question for you. How do you justify that pentagon, with, you know how many sides it has? How can pentagon not be a descendant class of rectangle? Pentagon is a subclass of polygon, but not rectangle. Why not? What kind of logical fallacy would you run into? Think about it. Do some.
The pentagon should have 5 sides.
Make it a little bit more mathematical for us. What would be the invariance for pentagon?
Invariant for pentagon is vertices that count to 5.
Good. And then? Yes.
And if we add the previous invariant for rectangle, which inherits,
Uh-huh.
then it cannot also be vertices of count to 4.
Exactly. Exactly. Okay, let's try this again. Okay, very good. That's exactly correct. So somehow we are trying to use logic to justify why one class cannot be the descendant class of the other using class invariance. Because somehow, if you try to accumulate all the invariant together, it's equivalent to false. Okay, which is bad. So now, if you think about it, over here, pentagon, the invariant will be vertices that count is equal to 5. And then for rectangle, vertices that count will be equal to 4. If you try to conjoin these together, what does that mean? Well, you will never get any satisfying pentagon, never ever. So this proves that pentagon should not be a descendant class of rectangle. Okay, guys, any questions? If no question, let me summarize in one slide, and then we can go on to the design pattern. Okay, so basically, when we talk about contracts in the context of inheritance, so we have the precondition and postcondition on both classes, right? So let's talk about pairwise. In the design time, when you're trying to do your design, either maybe on a compiler, iFor Studio, or just on the paper, you should really try to do the following exercise. You want to make sure the precondition in the superclass implies logically the precondition in the subclass. And when we say tautology, that means it's always true. Okay, you should prove that. Okay. And also, you want to make sure the postcondition in the subclass implies the original postcondition, right? That's something you can do, like a summary slides. And more than this, at the runtime, you should really know how iFor compiler is checking. You might be sometimes thinking, I actually try to make my precondition in the subclass more restrictive or less tolerance than the in the superclass. But why does this have no effects? That's exactly why. Because they will simply do the disjunction of the two Boolean conditions. That's why. At the runtime, what they will do is, for the original and new precondition, they will simply do disjunction to prevent disaster, to make sure there's no shock. And for the postcondition, they will do conjunction to make sure there's no shock, right? So this is kind of summarizes what you should know about contracts inheritance. But for rationale, you should refer to the previous slides. Okay? Questions? Okay, no questions? Okay, good. Are we ready for the state pattern? Okay. The state pattern is going to be very interesting. It's going to combine lots of knowledge about inheritance in a practical way. Okay, we'll talk about it. Okay. Anyone here who has learned state pattern before? That's good. I'm happy, right? That's good. It's completely new. Any one of you who has not taken 2001 so far? 2001, you know, the theory to theory of computation. Any one of you who has not taken that? Every one of you, right? We're going to use some NFA since it's about states. Okay, so now let's do it. Again, when we talk about design patterns, so these are general solution to a particular category of problems. So before we actually talk about a solution, let's understand what a problem is. Because by the end of the semester, you will have learned about maybe at least 6 different design patterns. So when I give you a question on the exam paper, I'll just give you the problem only. What you're going to do is to decide which pattern to use in order to solve it, right? So to really do this, you have to understand what this pattern is good for, and also you should not, of course, state pattern should not always be used, only under certain circumstances. Okay, and for your reading, you should really read OSC 2, chapter 20. Okay. Okay, this is a typical problem that you can solve using the state pattern. So this is actually like a simplified view over here, but I'll get to this view in just a moment. But any online booking system that you might have, for example, let's say here, it's a real website. So you can actually book some flights where you can specify the city and destination, and also one-way, multi-city, or whatever, right? So you can have different, and once you click on a particular option, they might bring you to a new page to ask you for more choices. And eventually, you can check out and then get a receipt, okay? So not just the cheap flights, you got Amazon, eBay, or Taobao, right? You got different websites you can support, web services, okay? It's a very practical pattern. Okay, so now let's go on. So now for the purpose of the lecture, let's assume we got the following system here. Let's say it's kind of like an online air tickets booking system. So you got things like, so let's say currently I'm now in a particular window or panel over here. I'm in a particular state. So over here, the computer is trying to learn from me. They're trying to inquire me about the flights. So I can say source should be Toronto, destination should be Zurich, etc., right? And then what's really important is for every state, they have different information to collect. Let's say for this particular state, we are trying to inquire about flights. So all the answers we give to the program will be flight related. For example, it's destination over here and source, and also the departure date and return dates. And then the second piece of information we need to give to the program is, how do we continue, right? So usually in the GUI, you can just click on next or previous, right? But now let's make it a little bit more explicit so you know what transitions you might have to support. You can type 0 to say, now I want to exit. Or you can type 1 for some help menu. Or you can type 2 for any further inquiry. Or you can type 3 to reserve a seat, okay? That's kind of the system we want to support. For example, let's say if I choose 1 and then hit enter, so it's going to bring me to another panel, and then it's going to display help-specific information there, okay? Any question about the kind of problem we are trying to solve, right? So that's kind of the problem domain for state pattern, okay? Now, for this kind of problem here, before we get to programming, because rather than showing to you the right solution right away, I'm going to show you bad solutions and let's try to criticize that, why they are bad. But now, for any, when you're trying to solve this kind of problem here, you want to draw a state transition diagram because you got different panels there. Each panel is like a different states. And for each state, you might have different actions. I want to say, for example, over here. Over here, you can see if I'm trying to inquire about the flights, I might choose to go to help. That's once I go to the help page, the only option I might have is to say, now go back to the original page, which is the inquiry on the flights. If I choose to say reserve a seat, and now once I go to the reservation page, now the only option I might have left will be either go back to the inquiry page or I can say confirm and issue the tickets, right? So depending on which state you are, you may have different operations to support. It really depends on the state. Okay. Now let's now assume the following state diagram. Of course, you gotta figure out the states and also transitions. But for this particular exercise, I give you the transition diagram already. In reality, you have to figure out the states by yourself, of course. Okay, let me just move on to the iPad and I'll try to go over the state with you. They're rather important. Okay, that's the state diagram I'm gonna use. For simplicity, if you read the OSC2 textbook, they also got a state called help. I just eliminated for its simplicity for the lecture, okay? But we still got sophisticated enough problem to solve. Okay, let's go over very quickly. The initial states is just called initial. Okay, I also number them. Okay, 1, 2, 3, 4, 5, 6. 6 states in total. Now here's a convention. So there are only 3 possible choices for, so here we talk about states, and we talk about choices. Choices simply means transitions. There are only 3 possible choices for the user. It can be either 1 or 2 or 3. So these are the only 3 choices, okay? Only 3 possible transitions. Now, let's say, I try this. Whenever the convention is, whenever you have 3, that means you want to move forward. If you have transition 2, that means you want to move backwards. For example, if I'm in 1, if I say 3 over here, that means I want to go to the next phase for the booking. And now I can inquire about the flights, and then I say 3 again. And then now I can inquire about the seats. And then I say 3 again, I can now reserve. And then I say 3 again, I can do confirmation. Okay? And then I say 3 again, I go back to the initial page. Right? So 3 simply means move forward. On the other hand, the 2 over here simply means to go backwards. So maybe I'm now in initial page, I can say 2, and I can simply go to the previous one that I just confirmed. Okay, something like that. Okay, so you can also get 2 over here, you get 2 over here, this direction here, 2 here, and 2 here. And the only place where you can say, now I don't want to continue with the interaction session anymore, I can simply say, let me use a different color here, 1 from state number 1, which means I go to the final one. Once you get to the final stage, that means the application terminates. Okay? Of course, as long as you don't really get to the final state, the session will continue for as long as the user wants. Okay, so it's interactive. Okay. Any question about the state diagram here before I move on to present to you the first solution? Okay. Okay, very good. Hopefully it's not too complicated. Okay, we'll certainly revisit this diagram in just a moment. Okay. Okay, let's talk about what's the challenge for this particular problem here. What's the design challenges? And then we'll present to you different solutions. Okay. The first challenge is, since we talk about the state transition diagram, the one I just gave to you has only 6 states and then about 15 transitions. But in principle, in the very realistic application, the number of states, you shouldn't be too surprised if the number of states may be 100, 200, or even 300, or even more, right? What about the number of transitions? As you learned in 2011, if I have the number of states being n, what's the worst case for the number of transitions? About the complexity of the graph, right? Which is, say that again, n times? Okay, which is bigger of n squared, right? Which means when you get n states, you may get in principle up to n squared transitions. That's as complicated as you can get to. Okay, that's what you learned from 2011. I'm just trying to link that to the knowledge there. Okay, so first challenge is the diagram might be very complicated. So your last choice is to try to hard code this particular diagram into your program directly. You will see that in the first solution, that's what it does. And we have to criticize that. Number 2, and the graph structure is subject to extensions modification. That's actually very realistic requirements. Again, whenever you're doing software projects, it's not that once you deliver for the version number 1, it's done. No, you gotta maintain that. Whenever you want to extend for a new page or a new functionality, you have to be actually flexible. Okay? So now, for example, let's go back to the diagram over here. Let's say over here. Let's say what we want to do is we want to somehow collapse these 2 states together. Let's say we want to have a single inquiry page about the flights and the seats. In this case, we got to delete certain states, right? In this case, what we got to do is, for example, we might say delete this particular state over here, and then we somehow want to merge their transitions, right? Whatever they used to go to here, maybe you have to do something like that, and then something like that, right? Conceptually speaking. But how do you support this in your programming language or design language? That's a challenge. When your diagram is actually pretty large, and when you got lots of dependency ongoing and incoming transitions, how do you maintain that? That's a challenge. Okay? You get this point? So let me just undo this. Okay, you get the idea. And also, how do you add a new state, for example? If I simply just want to add a new state to ask about the customer's dietary requirements, and how do you put that state in your program and then assign also the corresponding transitions there? That's also a challenge. Okay? Now, this is the most important thing because this kind of system is actually quite pervasive. You got lots of online booking system, eBay, Amazon, Taobao, or any even registration system. As long as you have a notion of states and trying to traverse between pages and try to see for each particular page, you got to do page-specific actions. In that case, it will be applicable to the state pattern. You don't want to say for every such problem, I need to design a completely different solution. Well, we want to have some reusable solution. That's why we need design patterns. Okay. Okay, so you can. I also got links over there, so you can feel free to get a feel about what this kind of a system is. Any questions until now? So far, we just talked about problems and the challenges we have. Okay. Well, what I assume when you solve this problem here, you are able to, based on the problem statement there, to draw the corresponding state transition diagram. Okay. And once you get a state transition diagram, how do we translate that into programming artifacts? Okay. That's the challenge. Okay. Let's see the first solution. First solution. We got 3 solutions in total. The state pattern is the last one. Okay. let's try to get through at least the first two, because the first two you might more or less try to solve that in that way. You want to know why they are bad, okay? The first one I'm trying to use a little bit old-fashioned notation called label. So for example, for those of you who programmed in C before, in C you can put labels and go to statement, right? So that's the first solution, okay? Let's see how the first solution works. Basically, since we have 6 different states, what I would do is, for each particular state, I'm going to create a label section there. For example, I will have you can see the first state is called initial. I simply have a block under the label called 1 initial and then colon. That's how you declare labels in C-like language. And then I'm going to do some action over here under this particular label. Okay? So I can always go to this particular label and then do something specific to it. Right? That's kind of state dependent. And then I'm going to do the same thing for the second states, third states, fourth, fifth, and sixth. So that's kind of the overall structure for your the first solution. You just got lots of label depending on how many states you have. If you have 6 states, you're going to have 6 label sections. If you've got 100, you have 100. Okay. Now let's try to look at the more detail. How does this particular each particular label section looks pretty much similar? Let's see how they look like. Okay. Now we want to know if somehow I go to this particular label section, what am I going to do? Okay, let's go over that. Okay. So once I go to this label here, the following is going to be executed. First of all, I say I'm going to run a loop. Okay? I will say, first of all, before I go into the iteration, I'm going to display some seed inquiry panel, which means this display tells the user now you are in this particular page. Okay? And then, when am I going to stop the execution? Basically, this page, the idea is I'm going to read some input from the user in order to process some information. As long as the user's information is not accurate, for example, they're supposed to enter some number, but they actually enter some alphabets. In that case, we're going to tell them you got some errors, you got to try again. Okay? We keep doing this until the user gives us the right information for 2 things. One is, so for the convention here, I just called it answer and choice. Answer simply means, if we talk about seed inquiry panel, the answer can be, tell me what's your departure dates, what's your return dates, and these dates must be valid, of course. You got to choose a valid dates. And also the return date must be larger than or equal to departure dates, right? Things like that. And what about wrong choice? Wrong choice means if the user is now done with this particular page, they got a choice to go to somewhere. They can either choose to go to help page, or they can choose to exit from the application, or they can choose to confirm with their booking, right? So they got choices. Anytime they choose something that they are not expected for this particular page, they'll be given errors as well, okay? So we keep doing this until we don't have any wrong answer and we don't have any wrong choice. Now, so of course, we'll keep reading users' answer for the current panel, and we also read their choice, okay? And the choice, let's say, is a number. It can be 0, 1, 2, 3 in this case. And now we say that if it's either a wrong answer or it's a wrong choice, then we'll simply output some error message, okay? So it's mainly just pseudocode, just to get the idea. And now, let's say we can exit from the loop. What does that mean? That means both the answer and the choice are valid. That's why we exit from the loop. After this, we process the answer. Let's say they enter the valid dates for departure and return. So we can somehow connect to the database and try to inquire about availability, etc. And then, depending on what the user wants, let's say for this particular seed inquiry panel, let's see this. If you see seed inquiry over here, this is state number 3. What outgoing transition do we have? You can either go through number 2, back to state number 2, or you can go for action number 3, and then you go to state number 4. You only got these 2 options. These are the only 2 options you have. In that case, if you go back there, you can either say, if the choice happens to be 2, in that case, I will go to the action block for 2 over here, and then start the same pattern again. Or if the user's choice is actually 3, in that case, I will go to the block for number 4 over here, right? Just basically the next block over here. Any question about this first attempt? Before we try to criticize it, let's try to think about what's a good thing about it.
It guarantees correctness.
Correctness, because I would, yeah, actually in some way I agree. Correctness in the sense that it's pretty much like a exact reflection of what you have in the state diagram over there, right? It's pretty much obvious for you to see that over here, 1, 2, 3, 4, 5, 6, they correspond to exactly 1, 2, 3, 4, 5, 6 over here, right? And each block over here tells you exactly what each state will do. Also the outgoing transition that might go out. That's a good thing. It's very straightforward. It's very naive. If you got the project due tomorrow, this will be a solution you want to go. And assuming that you will never touch it again. Okay, let's criticize. Apparently, it's not a good design. We got at least 4 to 5 points to criticize about it. Let's try, okay? I'll give you a little bit hints to think about it. First of all, runtime execution. When you try to run this software at a runtime, would it be easy to debug or predict what's going to happen? Would it be easy? Let me give you some idea, okay? Before I introduce you to the term, okay? Let's have a look at, okay, over here, at the runtime, okay? Let me now use the blue color, maybe red. Let me use the red color over here to tell you the flow of execution. Let's say we start with initial states. We do something here, and then somehow the user choose to go to maybe 2. Okay, let me just draw a little bit better to illustrate my point better. Let's say at the end of 1, we go to 2. And then from 2, we go to 4. From 4, we go back to 1. And from that, we go to maybe 5 in general, right? Because any transition is possible. And then from 5, we go to 6. And then from 6, we go to 4. There is a very famous term for this. I'm not sure if you have heard about this. It's called spaghetti code. Okay? So this means the way you can see exactly the way I draw it, right? So at the execution, you simply just go one place and then to another, and then to another. You just got so intertwined flows of execution. It's very difficult to debug. Okay, okay, that's one criticism. Okay. That's also why the assembly code is usually very difficult to debug, because you got labels. That's the way you encode the iterations, right? To say, go to this label, and then if something is true, you go back to the label again to simulate iterations. Yeah. That's the first drawback for this design. It's simply too difficult to really keep track of. Now we only have 6 states. Imagine if you have 500 states. What would you do? It's very difficult. Okay, what about transitions? Okay. You can see that, so this one, you have to see that the other 2 designs to a little bit appreciate what this point is trying to say. I'll try to explain a little bit over here. You can see the way you can see that this is the whole program over here. You can imagine that we kind of do this whole thing in a single class over there. And you can see that this is it, right? We don't have any other classes to be interacting with it. That's it. So the whole control structure for your class is defined over here in a single class. Okay? This is not so good in terms of for extensibility for your program, because later on, let's say if you want to add more states into your program, what you got to do is you have to somehow go into a particular label block and then change the way things are going to behave. So you're going to change the way also the flow of execution is going to work. So that one, you're touching the control structure for your program too often. That is not so very recommended. Okay, I will reserve this point a little bit. So later on when we talk about the other 2 designs, you can compare. Okay. Okay, another thing is about reusability of your code. Okay, this one here. can you see, okay, here I only show you block number 3. Can you imagine how the other 5 blocks are going to look like? Are they going to look like similar or very different, structure-wise? Similar, right? Because it basically, let's say for number 4, let's say we go to number 4, how would you define the block for reservation panel? You still have to display the reservation panel to begin with, and then you're going to say until all the answers and choices are valid, I'm going to keep asking the user to enter the answer and also the choice. And then I'm going to process the answer, and then I also going to do some case statement over here to say if it is this, go there, if it is this, and go there. Lots of repetition for the same pattern over and over again. If you got 1,000 states, you can repeat this 1,000 times. Remember what I said in the very beginning of the class. What does this mean? That means your design smells when you get duplication. Okay? That's just another point. Okay? Okay, now, one more. What about the branching structure for the design? So you can see that the way we, okay, let me just show you this point directly. Let's try to read this point here. The way we actually code this particular program over here, it's directly corresponding to this state transition diagram, which means now, if I say now, let's code another online booking system, which has a totally different state diagram. In that case, you can reuse very little about what you have defined so far, because the way we do state transitions, the way we do processing is completely different. It's basically nothing you can reuse over there. Okay? So that's why the first one is also not a general solution. Okay? It's not reusable. Every time you change from one application to another, you just cannot reuse all the blocks you have, because those blocks are specific to the transition diagrams you have, right? Once you change this transition diagram, they cannot be reused, okay? Especially the way you do transitions, right? Okay, so these are at least the drawbacks for the first design. It's pretty bad, okay? Even though it's quick and straightforward. Okay? Any question about this before I move on to the second design? Okay? Okay, let's now move on to the second one. The second one is actually better. I think the second one might be more or less what most of you or many of you will actually run into. Okay? The second one is not too bad, but we still see some smell over there in the design. We'll see why. Okay? And the second one also is called top-down hierarchical, and also one thing I didn't say here is not OO. It's not really exploiting the object orientation features a lot. What's object orientation? Inheritance, polymorphism, dynamic binding. You wouldn't see that kind of stuff over here in the second design. We'll try to improve that to move on to the third design. Let's see the second one quickly. So now, for the second one, what we want to improve, first of all, we want to make sure we don't really have the whole program structure directly correspond to the transition diagram. Okay? That will actually make your design too vulnerable to any changes later. So what we want to do is, let's try to do the following. Let's say we have an attribute called transition. In that case, the transition there is actually going to take some source state and also take some choice and then tell us what the returning state is, the target state is. Okay? For example, let me give you one example right away. So now let's say you go to here. If you try to call transition over here, and then I say from 1, I say 3. And this should return back to me 2. Right? That's kind of the transition function you're used to. I think maybe in 2001 you called this delta, right? Right? Okay, that's good. Yeah, just to draw some connection. Okay, very good. That's the transition function. And for this particular example, we simply say we can write some contracts very quickly. You can try to elaborate that later, but for now, I say this source state must be valid, should be between 1 and 6, and also target state should be between 1 and 6, and you only got 3 choices there, so that's between 1 and 3. Okay. Now, after this, how do we actually try to encode the transitions there? For example, over here, you can see that we got transition from 1 to 3, we got 2. So this is encoding this particular transition. But we got about 15 different transitions here. So how do we do that? Of course, one way naively to do it is you can simply say, let's say this make this a query. And then you can say if the source equals 1 and the choice is 3, and then return maybe 2, for example, right? You can get lots of if then else statement there, but that's not the best way to go. Any suggestion for implementing this transition? Not too sure if we talk about this in 2001, but they do mention about some keyword. Okay, let me give you some idea over here. Oh, actually, I already said it here, right? You got two-dimensional array. Why? How do we present all the transitions in a systematic manner? You have something called transition table, right? Let me show you what that looks like. That looks like this. For example, let's see over here. Well, and this is why two-dimensional array is a very appropriate candidate for implementing this. Let's say we got two-dimensional array, and the row over here, we got 6 rows over here because we got 6 different states. So 1, 2, 3, 4, 5, 6. Okay? And then for the choices you might have will be 1, 2, and 3. Only 3 choices. So in total, we are implementing this using 18 entries. Okay? Now, for example, let's say over here, how do we fill in the transitions? I'll show you that at the end. For example, you can see if I'm currently in state number 1, I'm taking choice 1. I should move on to 6, right? So if I'm in state number 1, I'm taking choice 1. I will go to 6. Okay, that's exactly the transition I can encode. Questions until now? Okay. So far, this is already better than the first attempt. In the first attempt, we encode all the transitions directly into the blocks. But now we try to separate this out into a two-dimensional array. So every time we want to query about the information about moving from one state to another, we can always ask about this transition table, this two-dimensional array. Okay? And question for you. Let's say this is also more reusable. Okay? Let's say, so now we got 2 parts. We got transition table and also everything else. Okay? You will see that everything else works pretty much generally, which means everything else can be reused. Only the transition table has to be changed when you move from one application to another. Okay? We'll see that in just a moment. Okay, any questions before I move on? Okay? First thing you should know that we are trying to support this using a two-dimensional array. And if you look at the course website, I also uploaded some source code for you to play with. So that one includes the state pattern for the third solution. Okay? Okay, so now for this one here, let's talk about the good part about this solution. It's a more general solution compared with the first one because you'll see that so somehow state transition is separated from the rest of the program, okay, which is good. And also we'll see that it's actually quite reusable, as we will see. Okay? You will see just apart from the transition itself, everything else, the way we control how we interact with the user, re-input from them, process the answer, they are very general. It can be certainly adapted to other applications quite easily. Okay. Let's see something over here. So this is the overall picture for this design over here. Okay, I'll try to explain to you. Over here, there's a transition diagram. We'll come back here in just a moment. Okay. Oh, do I have that? Oh, I don't have that. Okay, let's try to just see the diagram. I think it's clear enough. The reason that we call it top-down and also hierarchical is because we have different levels, right? Level number 1, we are trying to execute some interactive session with the user until the user wants to exit. At the top level, just a session. And the session can be divided into different stages. Stage number 1, we want to have some initial state to start with. And then we can make transition from maybe from state number 1 to number 5, and 5 to 7, making transition. And then this part here is the meat for the solution. How do we handle each particular states? Let's say we are now in the confirmation page. What we got to do is When we want to execute this particular confirmation state, we have to take some information from the user, maybe their credit card information, or if they're a member of the company, they should really enter the membership number, and etc. And then I'll get to this stage in just a moment. And then after that, you have to finally check if the final state we have, the state that we transit into has reached this particular state. Because once we reach this state, that means we are done for this particular interaction. Okay. Now, let's see what this really is. When we are trying to handle a particular state, they are also can be divided into different sub-stages. That's why we got another level. So that's why you can see level 3, 2, and 1. We got 3 different levels. And also it's top-down, right? You can think of each one of them is like a routine call. You can think of execute session is going to call different functions. Function number 1, initial, transition, execute states, which will in turn call another function called display, read, correct, and etc. Okay? Let's try to go over this very quickly. The way we handle each state has a general pattern. This is how we handle that. First of all, we display anything that's specific to this particular panel or states. And then we try to read certain input from the user. They answer credit card information or departure dates. And then we try to validate their answers, whether there's a valid departure dates or if that credit card number is valid, etc. And then we say that if anything that's not correct, anything that's not valid, we'll output to the panel to tell them you enter something that's wrong. You should really try it again. Otherwise, we cannot move on. Or if the information that user has entered is correct, they can go ahead and process, maybe to charge their credit card or to try to inquire about the availability for the specified return and departure dates, etc. Okay? Any question about this diagram here? Okay? And then we're going to show you some code to make it more concrete. Okay? You can see that it's a tree, it's not a graph, which means that you cannot go back to the previous level, right? That's why it's a tree. Okay, let's try to see. So now we're going to focus on especially execute session over here at the top level here, and also execute states. We're going to see how they look like, okay, to get an idea. The good thing is their structure is pretty much general, so they can be reused for other applications as well. However, we'll see also some drawback. Okay, so now let's see over here. This is the idea. For every interactive session with the user, we have to start with some initial states. And then we have to repeatedly take input from the user, validate the inputs, and we only continue to the next state where everything's valid and everything's processed. Okay, let's see the code very quickly. So that's the execute session over here. So let's say over here we got current states. Remember we use number to represent the states. Again, we got 1, 2, 3, 4, 5, 6 different states. Okay, and now we also got choice, which can be 1 or 2 or 3. Now, over here we can say that we can again run a loop to say starting from the current state being the initial states, which can be 1, for example, until the current state is actually the final states. In this case, the final state should be number 6, right? And then each iteration there we do several things. First of all, let's try to execute the states. And execute the state, you can now see that we go from, you can execute state. So in the context of execute session there, we try to call execute states. Let me show you the diagram again. When we are trying to do this execute session here, somewhere along the line, we try to call execute states, which is a helper method call, right? And then after that, we're going to go to the next level, level 1. Okay? Let's just continue. And then after execute the state, which I'll show you in detail in just a moment, what it will tell me is, it's going to tell me what a choice is for the user. Okay? Now, let's say, for example, let's say I'm now currently in this state over here. I'm now here. So the current states is number 4. Let's say the choice for the user is, So what choices can they have? They can either go for number 3 or they can go to number 2. Let's say they chose to go for number 3. So what we will do for now is we're going to call the transition function. You can see transition here. Remember we just said before, we can support the transition function using a 2-dimensional array. You can just query about the number of rows is going to correspond to the number of states. Number of columns is going to correspond to the number of choices. Okay? So now, what we will do is you can say transition, the current state is 4, the choice is 3. In this case, what it will return is 5. Right? Returns 5. Okay? That's what you would do over here. And once we know what the current state is, we can go back to check the exit condition over here, right? If the current state happens to be the final state, then we exit, we're done. Otherwise, we keep going, okay? Keep going for each state. Any question about this top level feature? What I just have shown you is the complete details for this particular feature over here, execute session, just that. Before I move on to execute states, I just want to see if there's any questions. Okay, we haven't, in some way trying to really understand the attempt number 1 and number 2 is quite necessary. You want to know why they are bad, right? But once we go to the third solution, we'll see that how elegant it is. Yes?
Go back to the final
Okay. Okay, let's say this. The question, let me try to guess what your question might be. You can see that we say that we keep doing the iteration until it's final. It's final is something that we define. Maybe I'll define that aside. I'll do that right away. And depending on what the current state is. Okay, let's see one example here. What you can have is something like this. Is final, and then it's going to take some states S. Okay, you can simply say it's going to return some Boolean. You can say result is a sign. S equals simply just 6 in this case, right? That means we're done. Okay. So now, let's say for the example I just showed you, after we do the transition over here, you can see after we say current state is updated using the transition, right? And then we got to go back to the loop, pretty much like how you do the while loop or for loop in the Java, right? So now let's check again. Let me just go back to the diagram here. Let's say we used to say starting from state number 4 over here, and the user made a choice number 3, which is over here. Starting from 4, making a choice for 3, the target state should be state number 5, right? So now for the 5 over here, we're asking the similar question, the following question: is final and then 5. Is this true or false? False. And false, that means this state is not the final state, so the interaction should keep going. Let me give you another example. Let's say if the current state is actually, let's say 1, and then the user choose 1, right? 1 here, and then user choose 1 over here. Now, what a transition will do, 1 and 1, is going to give you 6. Now you go back to that until condition over there. So now 6 is final 6. That will be true. That means we exit from the loop. We are done. That's from the top level. So it's like a keep moving between the states in the diagram until you reach the final states. Of course, in principle, for any NFA or DFA, you may have more than one final states, but there's only a unique single initial states. Okay? Guys, any questions here? Okay. Okay, let's try to go over the second routine, which is also important. Okay. What we just have gone through was execute session. Let's talk about execute states. For each state, for each current state, how do we handle that states? So whatever current state you figure out over here, you're going to pass that into execute states. Okay. Now let's see how the execute state is going to work. Okay, execute states. given the current states, which can be 1, 2, 3, 4, 5, 6, like the 5, 6, one of the 6 over here. And you're going to return some integer just to tell us where the user want to move. Okay? And also this pattern here is also very general. We're going to have some answer from the user, credit card information, departure dates, return dates, and whether the answer is valid or not, and also the choice. Okay? Let's see the following. Again, we're going to run a loop to handle the states, right? As long as the user's the answers or choice is not valid, we're going to keep going. We're going to keep trying, keep prompting them to enter. Until the answer from user is valid, we're going to do the following. First of all, display the current states. Just say what the current state is. And then you're going to read the answer from the user, and also you're going to read the choice they make, and also you're going to validate the choice using the correct feature here. Okay? And then also, if the answer is not correct or not valid, you're going to put some error message over here. Okay? And as soon as the answer becomes valid, we're going to exit from the loop, and then we go to process the current states using the answer we got, which is guaranteed to be valid. And then we can assign the user's choice to be a result. So this pattern here is going to be very similar for every state that we're going to handle. And this is not application specific. Any application you want to support, all you got to do is you want to make sure all the green parts are defined properly. Okay? Can you already see some drawback for this code over here? Focus on the visual hints I'm giving to you. Okay? Well, you can see that display, read answer, read choice, correct message, and process. All of them take a common argument called current states. We are simply passing around the current states around all the features in the level 1, the bottom level there. So this is not a good sign for the design. Okay? We actually see this on Wednesday. Okay? Do we have more time, or are we okay? We're okay, right? Do we have more time?
We're at 49.
Okay, 49. Okay, good. Let me just say something about the lab test. I will say the following.